Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called optimal design of fracking oil and gas shale production networks. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. The problem to be addressed in this lecture is related to reservoir recovery optimization. It includes overall investment optimization, and secondary recovery programs, and concentrates on oil fracking and shale gas recovery. Fracking oil and shale gas. What is shale gas? Also known as shale gas, it is natural gas that is trapped in rocky sediments abundant in shale and other organic materials, at depths of 1,000 to 5,000 meters. It can exist on the same plate as petroleum and other hydrocarbons. Since the gas is trapped in shale sediments, its extraction is carried out using the hydraulic fracturing or fracking technique. This technique begins with the drilling of a vertical well that, once the desired depth has been reached, is accompanied by a horizontal drilling that can extend between 1 and 1.5 kilometers. This type of drilling is repeated in different directions, starting from the same initial vertical hole. Once drilling is done, and due to the low permeability of shale rock, it is necessary to fracture the rock by injecting a mixture of water, sand and chemicals at high pressure, to allow the flow and exit of the gas. The flow decreases very quickly, so to maintain production it is necessary to continuously perform the hydraulic fracturing procedure in the same wellbore. The most important socio-environmental impact of shale gas exploitation is concentrated in the decrease in the availability of water for humans and ecosystems. Between 9 and 29 million liters are required for the annual fracturing of a single well. The exploitation of 20,000 wells per year would mean an equivalent volume of water between 4.9 and 15.9 million people in a year. The steps to carry out the fracking process are: chemicals, water and sand are injected at high pressure. Pressure causes fissures in rock so gas flows back out, and methane and flowback water are recovered. What is the difference between conventional and unconventional gas? The terms conventional gas and unconventional are often misunderstood and have taken on different meanings in the gas industry. Conventional gas can be developed with a limited number of wells due to the accumulation of hydrocarbons in a confined area, with well-connected pore spaces within the bedrock, which allow effective drainage from strategically located wells. The gas flows to the surface under its own pressure, driven by a water table under an expanding pressurized gas layer that covers the gas. In contrast, with unconventional gas, the source rocks that contain the gas have much lower porosity, i.e., the void spaces between the grains that make up the rock are very small, and much lower permeability, i.e., the interconnection of pore spaces to allow gas to pass through the rock is very low. Therefore, artificial stimulation, such as hydraulic fracturing, must be employed to generate the gas flow. Conventional gas production has been improved and many of these techniques have been refined and applied to unconventional gas. Horizontal drilling and hydraulic fracturing have been used for decades in conventional reservoirs, but increased efficiency and accuracy have allowed this technology to be employed in unconventional gas reservoirs, making them economically viable. The figure shows a schematic diagram showing typical well construction, casing, and horizontal drilling for shale gas extraction. Shale gas is mainly methane trapped within sedimentary, clay-rich rock at depths greater than 1,500 meters. The low permeability of the rock means that the gas, whether absorbed or freeform, in the pores of the rock, cannot flow easily. To extract shale gas, wells are drilled at depths of between 1,500 and 4,000 meters through several layers of rock to access the shale. The wells are lined with steel and cement adapted to their purpose, designed to protect the groundwater from contamination. To maximize shale gas recovery, a technique called horizontal drilling is used. This technique usually involves the well changing from vertical to horizontal direction deep underground, away from any aquifer. Showing how fracking for shale gas oil works. First, the earth is drilled to reach the area where the shale gas oil is located. The high-pressure mixture is then directed towards the rock to release the gas/oil and thus flow to the surface and be extracted for energy purposes. The figure shows a schematic of a typical fracking field. Small fissures are created that release the gas and then flow down the pipe, digging into the ground and being stored on the surface in containers. The sand ensures that cracks, once opened, do not close so that oil and gas can flow for a long time after fracturing. Once the fracturing is complete, the constructions are removed and the well is sealed. Fracking fluids are typically pumped deep into the ground and stored there indefinitely. The shale fracking process is shown in the image. Hole drilled onto shake rock, water, sand and chemical pumped into borehole, pressure in bore causes fractures in shale, and gas from shale flows into pipe and back to surface. Produced water can be used in irrigation, municipal, industry, surface water, groundwater, and hydraulic fracking. Competition between these uses must be considered in any fracking project. Shale gas development project in the Marcellus Shale play. Optimization of investment, drilling, and water management in shale gas supply chains. Challenge: due to the importance of the topic, HI is researching an optimization of investment, drilling, and water management in shale gas supply chains, so that it can offer oil companies its services on this issue. Solution: this type of oil projects is subject to the following constraints. Shale gas production: the number of wells previously drilled in a pad determines the shale gas production at every period, while methane, ethane and other NGLs produced at the well pads are directly obtained from the shale gas composition. Flow balances: stream flows from well pads converge to junction nodes, where they are compressed and diverted to processing plants. Flow balances at junction nodes and separation plants are imposed. Sizing plants, pipelines and compressors, separation plants construction and expansion, as well as the installation of new pipelines and compressors, are monitored over the planning horizon. This permits to track the shale gas processing capacity, the maximum flows in pipelines, and the compression power. Water supplies: water sources for fracturing new wells are strategically allocated to well pads so as to comply with their limited water availability. Maximum demands: dry gas and NGLs have limited demands from nearby markets. Real-world case study: shale gas development project in the Marcellus Shale play. A shale gas production company is interested in expanding the drilling and production activity in the Marcellus Shale play. The company has determined more than 150 potential sites for well pads, which can be grouped into 9 regions. All the shale gas produced in each region is collected by a low-pressure trunk pipeline that transports the gas to a nearby compressor station. Finally, the raw gas is dehydrated and sent through high-pressure transmission pipelines tied to midstream lines owned by third-party distribution companies. Pipeline construction and compressor installation require considerable lead times, more than 2 years, which are considered in the formulation. In addition, the company has the possibility of drilling the wells and keeping them closed for some periods until the pipelines collecting the shale gas become available. Besides, a maximum of 4 wells per pad can be drilled and completed in a single period, up to 12 wells in at most 3 pads per period, and each pad should not contain more than 10 wells. 14 freshwater reservoirs are available in the area. Due to confidentiality reasons, further details on the problem cannot be given. Since the shale gas is dry, 95% mole methane, the study does not account for gas processing and fractionation plants. The Marcellus, Point Pleasant and Utica are extensive formations that cover parts of Kentucky, Maryland, New York, Ohio, Pennsylvania, Virginia, and West Virginia. In 2011, the USGS estimated a mean of 84 trillion cubic feet of natural gas in the Marcellus Shale, and in 2012 the USGS estimated about 38 trillion cubic feet of natural gas in the Utica Shale. This is a significant increase from the previous USGS assessments of both formations. The pink dots indicate possible shale gas extraction points. The figure shows 48 states with shale gas in United States. Fracking's environmental footprint transform Pennsylvania landscape. The Marcellus Shale contains an estimated 1.5 billion barrels of natural gas liquids, while the Point Pleasant Utica Shale contains an estimated 1.8 billion barrels of oil and 985 million barrels of natural gas liquids. Natural gas liquids are liquid hydrocarbons like propane, butane or ethane. Most of the drilling activity at Utica is located east of the Great Lakes, but shale was first discovered in Quebec. Forest Oil officially announced the discovery in April 2008, with 2 vertical wells producing 1 MMscfd at depths of 4,800 feet. Talisman Energy began operations in Quebec Utica the following year, but overall activity was limited. The province of Quebec all but put an end to new drilling opportunities when it issued a moratorium on hydraulic fracturing in March 2012. Currently, New York and Maryland have similar restrictions. During exploratory phases in Quebec, Chesapeake Energy claimed a discovery in Utica, Ohio, in September 2011. Its 4 completed wells had an average depth of 5,280 feet, and 3 wells in the liquid-rich part had average yields of 2051 barrels of oil equivalent per day, The other well in the dry gas window peaked at 6.4 mmcf/d. Chesapeake Energy management as world-class and acquired approximately 619,000 gross acres, increasing activity through joint ventures by remaining the primary operator. While permits accelerated rapidly, as the Ohio Division of Natural Resources approved more than 1,000 permits between 2010 and 2013. A state report also credited Shale with increasing employment in the oil and gas sector by 30%, while offering wages 68% higher than the state median. Today, drilling productivity shows that Utica's gas production is 67% higher than that of the Bakken, and that its oil production exceeds that of Marcellus. Total gas production has grown at a compound monthly rate of 6% since January 2012. In March 2015, Seneca Resources announced a test well in Tioga County, PA returned an IP rate of 22.7 mmcf/d. The only catch was that the well was drilled to 12,200 feet and received 30 fracking stages, which may indicate how truly difficult it is to penetrate the rock. The results still present a measure of success, considering the Utica was initially believed to be predominantly in Ohio. Instead, it reaches all the way to northern Pennsylvania and is presumably economical in New York. The Utica's viability in Tioga County was confirmed by Royal Dutch Shell late in September 2014, with 2 test wells returning initial production rates of 11.2 and 26.5 mmcf/d, respectively. Shell increased its acreage in the region by more than 50% before announcing the results of the test wells. The figure shows the well producing from Marcellus Shale play. To solve the problem, a large-scale MIMP was developed. The large number of pads yields a large-scale model with 4,815 discrete variables, 12,226 continuous variables and 16,815 constraints. After 2 major iterations of the BRO algorithm and 71,000 CPUs of computational time, the problem was solved. The optimal solution yields an NPV of of American dollars, with a global optimality gap of 8.2%. The most convenient regions to be exploited during the following 10 years are 2 regions, where a total of 22 and 18 pads are constructed, respectively. Gathering pipelines of 7 to 10 inches in diameter collect the shale gas in each region, while trunk pipelines of 23 to 24 inches, and transmission pipelines of 12 inches, to delivery point 1, and 18 inches, to delivery point 2, are planned. Finally, a compressor station with a total power of 32,000 kilowatts should be installed. Freshwater for drilling and fracturing is supplied by 3 of the available reservoirs. The figure shows the schematic representation of the shale gas supply chain superstructure in the Marcellus Shale play. The most convenient regions to be exploited during the following 10 years are regions 2 and 6, as seen in the figure, where a total of 22 and 18 pads are constructed, respectively. Gathering pipelines of 7 to 10 inches in diameter collect the shale gas in each region, while trunk pipelines of 23 to 24 inches, and transmission pipelines of 12 inches to delivery point 1, and 18 inches to delivery point 2. A compressor station with a total power of 32,000 kilowatts should be installed. Freshwater for drilling and fracturing is supplied by 3 of the available reservoirs. The figure shows the number of wells drilled at every pad per period in the Marcellus Shale play. The figure shows the total number of wells drilled at every region. The figure shows the drilling strategy in the Marcellus Shale play. The figure shows the shale gas flows in the optimal solution of the Marcellus Shale play, that illustrates the shale gas flows in major pipelines for periods 14 to 40, showing the trend of the model toward maximizing the pipeline utilization, by maintaining a stable flow over time. Residents fear fracking for gas will cause permanent damage to their forests, state parks and agricultural fields, as well as their water and air. Design of fracking oil and shale gas production networks. A case study is solved to evaluate the effectiveness of the proposed optimization approach. The figure shows the location of the potential shale gas reserves, according to studies by Pemex. The production system configuration shown in the figure requires 2 storage pits, with capacities of 2,100 and 4,950 cubic meters, to prevent the produced water from leaving the well platforms. The treatment system is composed of 2 direct osmosis units, and a mechanical vapor compression plant, while the second storage system requires 3 units with capacities of 670, 4,950 and 700 cubic meters respectively, and the final disposal is an additional treatment. Analysis of the Pareto curve. The multi-objective optimization problem considers 2 objectives that contradict each other: total annual cost, TAC, versus total environmental damage, IMTAL. It is important to clarify that IMTAL represents an indirect measure of the pollutants removed by treatment technologies. When this objective is increased, the environmental impact decreases, but at the same time the TAC increases, due to the selection of more effective and more expensive treatment units. On the other hand, when the TAC is reduced, it generates a worse performance for IMTAL, reducing its value, but causing a greater environmental impact. Point A, green dot, represents the solution with the best performance for TAC, and the worst for IMTAL, while in the extreme opposite solution, at point C, red dot, TAC has the worst value, but IMTAL improves significantly. The Pareto curve considers an intermediate solution at point B, yellow dot. It should be noted that freshwater consumption is a key criterion, which plays an important role in the selection of the final design, which is associated with each solution belonging to the Pareto curve. The composition of the shale gas supply chain is the result of an optimization process. The figure exhibits the optimal distribution for the water streams to properly operate in point A. It should be noted that the freshwater is the main source to carry out the completion. The following section presents several papers in which Professor Ignacio Grossman and his team have participated at Carnegie Mellon University. Optimization models of optimal investment, drilling, and water management in shale gas supply chains. The paper provides an overview of 2014 optimization models for shale gas production. First describes a mixed integer optimization model for the design of shale gas infrastructures. It is aimed at optimizing the number of wells to drill, size and location of new gas processing plants, section and length of pipelines for gathering raw gas, delivering dry gas and natural gas liquids, power of gas compressors, and planning of freshwater consumption for well drilling and fracturing. Optimization models for water management in chemical processes and shale gas production. This thesis was submitted in partial fulfillment of the requirements for the degree of Doctor of Philosophy at Carnegie Mellon University. It is part of the previous paper. Strategic planning, design and development of the shale gas supply chain network. The long-term planning of the shale gas supply chain is a relevant problem. The paper presents a mixed integer nonlinear programming (MINLP) model to optimally determine the number of wells to drill at every location, the size of gas processing plants, the section and length of pipelines for gathering raw gas and delivering processed gas and byproducts, the power of gas compressors, and the amount of fresh water required from reservoirs for drilling and hydraulic fracturing to maximize the economics of the project. Mathematical programming models for shale oil and gas development, a review and perspective. The paper provides a comprehensive review of mathematical programming models for shale oil and gas development, and distinguishes contributions in 5 major topic areas, namely: development planning, water management, production optimization, supplies, gathering and processing, and life cycle analysis and sustainability. Environmental and economic water management and shale gas extraction. The paper presents the study of the life cycle impact assessment, LCIA, of water management and shale gas exploitation. The study includes the most common technologies for pretreatment and 3 different desalination technologies of recent interest: single and multiple effect evaporation with mechanical vapor recompression and membrane distillation. The results show that among these technologies, multiple effect evaporation with mechanical vapor recompression is the most suitable technology. A mixed integer linear programming by criterion optimization water management model address the profit maximization and the LCA minimization. Optimization models for shale gas water management. There are 4 key aspects for water use in hydraulic fracturing, including source water acquisition, wastewater production, reuse and recycle, and subsequent transportation, storage, and disposal. This work optimizes water use life cycle for well pads through a discrete time 2-stage stochastic mixed integer linear programming model under uncertain availability of water. The proposed models consider a long time horizon and multiple scenarios from historical data. 2 examples of the Marcellus Shale play are presented to illustrate the effectiveness of the formulation, and to identify optimization opportunities that can improve both the environmental impact and economical use of water. The main objective is to design the topology of the shale gas recovery network, establish the operating conditions of the network for the duration of its operation, guaranteeing the quality of the environment. Considering that the shale gas development problem is integer mixed nonlinear programming, MINLP, the proposed algorithm is based on 3 phases. Compositional junction pre-analysis, identify bounds for molar fractions based on given gas compositions to obtain good limits. Single delivery node problem, solve for a single delivery node MIP problem, to ensure feasibility and a good starting point for the next phase, and multiple delivery node problem, solve the nonlinear problem with an existing MINLP solver, such as the external approximation method, until the optimal one is reached. The shale gas development problem involves many discrete planning and design decisions that need to be addressed simultaneously. Optimal drilling strategy multiple delivery node problem. The optimal development schedule is characterized by many return to pad operations that maximize the overall equipment utilization. The optimization reveals that the optimal strategy could improve significantly the profitability of the gathering system. The image presents an example of the work carried out by the Center for Advanced Process Decision Making, CAPD, at Carnegie Mellon University for Carrizo Company that operates in the Marcellus Shale play. The case is made up of 14 well pads, 540 time periods, 2 impoundments, and 1 frac crew. Benefits of mathematical modeling compared to a heuristic solution, without exact mathematical models. The total cost is reduced by more than an order of magnitude, by 18.20%. The number of truck trips is reduced from 14,010 to 1350 trips, and CO2 emissions from trucking reduced from 630 to 60 metric tons. In 2015, the problem was solved with GAMS 24.0 and CLEX 12.5, on an Intel 2.93 GHz Core i7 CPU, with 4 GB memory, in 12 minutes of CPU. Optimization models for shale gas supply chains. The objective function is maximize net present value. Subject to the following constraints. Shale gas production, the number of wells previously drilled in a pad determines the shale gas production at every period, while methane, ethane and other NGLs produced at the well pads are directly obtained from the shale gas composition. Flow balances, stream flows from well pads converge to junction nodes, where they are compressed and diverted to processing plants. Flow balances at junction nodes and separation plants are imposed. Sizing plants, pipelines and compressors, separation plants construction and expansion, as well as the installation of new pipelines and compressors, are monitored over the planning horizon. This permits to track the shale gas processing capacity, the maximum flows in pipelines, and the compression power. Water supplies. Water sources for fracturing new wells are strategically allocated to well pads so as to comply with their limited water availability. Maximum demands. Dry gas and NGLs have limited demands from nearby markets. The figure shows a refinery process water system superstructure. The primary water sources are freshwater and purified water. In addition, crude oil often carries emulsified water source. 5 water-using process units are considered in this study. They are desalination, column condensation, steam generation, cooling water, and general consumption. The water quality and flow rate requirement of these processes are summarized in Table 3.12. The third water source, crude oil train, has a maximum flow rate of 15 tons/h, and the wastewater treatment plant can accept a maximum of 360 tons/h of wastewater. Reverse osmosis and ion exchange remove salt from the streams, and trickling filter and activated sludge are used to remove organic content of the streams. They can be considered as the third process water source. 2 sinks are considered for discharge, a centralized wastewater treatment facility on site in the nearby river. The water quality and flow rate requirement of these processes are summarized in Table 3.12. The objective of the model is to determine the fracturing schedule that minimizes costs for freshwater consumption, transportation, treatment, storage, and disposal. The shale gas supply chain superstructure comprises 9 potential sites for drilling wells, I1 to I9, 8 potential sites for junction compression nodes, J1 to J8, 3 possible sites for processing plant installation, P1 to P3, 3 methane demanding nodes, K1 to K3, 3 ethane demanding nodes, L1 to L3, and 3 freshwater sources, F1 to F3. The operational variables of the model are number of wells to drill, size and location of new gas processing plants, section and length of pipelines for gathering raw gas, delivering dry gas and natural gas liquids, power of gas compressors, and planning of freshwater consumption for well drilling and fracturing. Life cycle water use for well pads. The Cartesian coordinates of each site, in km, are given in Table 1. Distances between nodes for pipeline length and water transportation calculations are measured in Euclidean norm. The planning horizon comprises 40 quarters and the annual rate that was considered for discounting back cash flows is 13.5%. The methane price is assumed to be seasonal. No more than 3 wells can be drilled in a single location during 1 quarter, and a total of 20 wells is the maximum number permitted for a single well pad. Overall, a total of 180 wells can be drilled over the time horizon. Below is the notation used in the strategic planning, design and development of the shale gas supply chain network model. Subsequently, the model used is presented in a summarized way. The feasible region of the model is determined by a set of linear constraints. They are grouped into 5 blocks. Shale gas production, flow balances, plants, pipelines and compressors sizing, water supplies, and maximum demands. The number of wells drilled, fractured and completed in the multi-well pad I during the period T is represented by the variable NIT. Stream flows from a well pad to junction nodes. Shale gas production at a certain pad, during a period, is sent to one or more junction nodes, depending on the network design. Stream flows from a well pad to junction nodes. Shale gas production at a certain pad, during a period, is sent to one or more junction nodes, depending on the network design. The total processing capacity of a plant P at time T is given in M3 of shale gas per day, and can be calculated from its capacity at the previous period, T-1, plus the capacity expansion started at the beginning of period T-tau s. In other words, it is assumed that separation plants, installations and expansions, take tau s periods. The set of equations considered by the model are: upper bound on the shale gas flows converging to a separation plant, installation of gas pipelines, maximum gas flow between a pair of nodes. Installation of liquid pipelines, and maximum flow in liquid pipelines. A large amount of freshwater is required in the shale gas industry for the hydraulic fracturing of new wells. The model assumes that the total amount of water required by a single well during the drilling, fracturing, and completion processes is known but may depend on the well location. A critical model decision is where to sell the dry gas and the ethane flows produced by the shale gas processing plants. Every potential market, or demand node, is assumed to consume a maximum amount of product, dry gas for gas distributors, ethane for petrochemical plants, based on their own transportation or processing capacities. The objective function of the model is to maximize the net present value of the long-term planning. Piecewise linear approximation of concave cost functions. Given the nonlinear concave cost, accounting for the cost of a processing plant, pipeline, or compressor, it is simple to demonstrate that piecewise linear approximations provide valid underestimations. By replacing the nonlinear terms in the objective function with the piecewise linear approximations, the MILP model reduces into a MILP model yielding valid upper bounds for the global optimum of the original problem. A key decision is how to divide the variable domain, that is, how many intervals to consider. The finer the domain discretization, the closer is the upper bound to the actual objective value of the MILP, but also the higher is the CPU time required by the MILP, since the number of integer variables increases significantly. An illustrative example comparing two network designs is presented in the figure. Shale gas produced on two different well platforms, I1 and I2, is sent to a processing plant in two alternative ways. A. Through an intermediate junction node, J1, which requires a compressor station, but the pipes are smaller in diameter, and shorter than in option, B. Directly, through separate lines, which do not require a compressor. Typical values of suction and discharge pressures at each node are presented in the figure. The costs of pipes and compressors according to their size, usually determined by economies of scale functions, are key to determining which option is the most convenient. Freshwater consumption, mainly for hydraulic fracturing, is considered a fixed amount required during the drilling period, which depends on the location of the well pad, and the possibility of reusing the return water. The selection of optimal sources for water supply is the key decision of the model. Other operational matters such as the capture, treatment and final disposal of return water, as well as the planning of confinements and the stimulation of wells, are also part of the decisions, but are outside the scope of this work. The well productivity, measured in million of cubic meters per day, is represented by a piecewise constant function of the well age, given in quarters and the drill location. Moreover, the shale gas composition, and particularly its wetness, percent of hydrocarbons others than methane, are assumed to be known and independent the well site and its age. Shale gas productivity, in millions of cubic meters per day, in each well is modeled as a decreasing function of the age of the well. Two cases are considered. Example 1, in which shale gas water, its content, and composition are the same for all wells, and Example 2, in which the chemical composition of the water depends on the location of the well. The figure shows the optimal design for the shale gas supply chain network, and the strategic drilling plan for the example 1. The optimal design for the shale gas supply chain yields a NPV of $1,664.48 American dollars. The optimal solution determines that only one shale gas processing plant is installed at site P1, with a maximum capacity of 6.594 of shale gas per day and a total cost of $651.2 American dollars. Due to the economies of scale, the plant and all the pipelines are installed in the first period of the time horizon with no expansions planned over the first 10 years. Regarding shale gas compression power at junction nodes, 1,236 kilowatts, 706 kilowatts and 818 kilowatts are installed at nodes J4, J5 and J6, in that order. The selected destinations for methane and ethane are nodes K3 and L2, respectively. Methane is supplied by a gas pipeline of 74.33 kilometers length, and 17.5 inches in diameter, requiring a compressor of 2,428 kilowatts. Ethane is transported through a liquid pipeline of 5¾ inches in diameter. The maximum flow for both pipelines is reached in quarter T7 when the plant is operated at full capacity. The production level at the plant remains high for other 6 quarters, until the maximum number of wells at every pad, 20, is reached. The figure shows the well pad development timeline, that is divided in 4 phases. Site preparation, drilling, completion, and production. The figure shows the simultaneous optimization framework integrated by 2 networks: HEN, Heat Exchange Network, and WN, Water Network. The first step is to simultaneously optimize the economics of the flow sheet as well as the cost of HEN and WN targets subject to process constraints. The first step then fixes the operating conditions of the flow sheet. The second step is to determine the detailed HEN and WN structures, and corresponding capital and utility costs using the fixed heat capacity flow rate, inlet and outlet temperatures, and water using process unit flow rates. The horizontal portion of the well is fractured in several stages, which require a fixed volume of water, which is obtained from freshwater sources and stored in freshwater reservoirs. Sand, 8.96%, and chemical additives, 0.44%, are then added to the water to form the fracturing fluid. Stage 1, located near the end of the well, is stimulated first, and the stage is temporarily capped to prevent its return, and Stage 2 follows Stage 1, and the process is repeated along the entire horizontal part of the well, until the last stage is completed. The figure shows A. Shortcut model, and B. Simplified model. To make the comparison on the same basis to demonstrate the advantage of using shortcut models versus simplified models, the first step is to optimize the WN structure with a simplified model, then in the second step, the WN with shortcut model is optimized with fixed network structure from step 1. The main difference is that the treatment unit is reverse osmosis for the simplified model WN, and ion exchange for the shortcut model WN. The figure shows the methanol synthesis simultaneous optimization. A. WN, and B. HEN. The table presents the data for structures by stages. 10 variations of the original problem will be considered. To model this problem, we rely on the superstructure representation shown in figure to account for the alternatives of interest. In addition to the freshwater acquisition structure from problem 1, we have additional treatment units for removing the total suspended solids, TSS, in the flowback water, a set of frac tanks at each well pad to store incoming wastewater, and finally, the unused flowback water a given well pad can dispose. In terms of the State Task Network, STN, the treatment facilities represent additional tasks, while the treated wastewater corresponds to additional states. The major assumptions for problem 2 are as follows. Freshwater trucking cost is only volume dependent. Wastewater trucking cost is volume and distance dependent to allow for recycling among geographically proximate well pads. The wells on each well pad are aggregated. ARP's decline curve is used to estimate gas production profile. A fixed percentage of total water used in fracturing must be freshwater. Only the first 2 weeks of flowback water can be treated and recycled, and there are existing temporary wastewater piping connections between a selected set of well pads and treatment facilities. The figure shows for scenario 3 the availability of fresh water and the cumulative use of trucks. Both the optimal schedule and heuristic schedule are shown in the figure. In the optimal solution, all well pads are stimulated under the fastest completion rate, and in the heuristic schedule, most well pads are stimulated at a slower pace. The heuristic program generates the least benefit over the 3-year period. In the optimal solution, all well pads are stimulated with the fastest completion rate. In the model, it is assumed that the desalination facility could be shared by other operators, who have around 200 wells to be completed during the same period. Considering that desalination is not a common practice in Utica, it is interesting to note that the cost of scenario 2, without desalination, is 52% higher than the optimum. Scenario 4 assumes that the rate of return doubles compared to the rate of return in the optimal case. The total water-related cost increases by 21%, which is expected as the cost of wastewater management increases significantly. However, the cost of pumping in Scenario 4 is lower compared to the optimal case, between $38.9 and $41.8 million of American dollars, as Scenario 4 takes advantage of recycling from the high rate of return. 3 technologies are analyzed in each case. CMVR, single effect evaporation with mechanical vapor recompression, MEMVR, multiple effect evaporation with mechanical vapor recompression, and MD, membrane distillation. The total LCO associated with the wastewater process reaches approximately 73.2 points per cubic meter of treated water using MD technology, and this impact reaches approximately 6.0 points per cubic meter treated MEMVR, which is around 91.8% lower. This result is due to the use of steam needed as the driving force in MD. MD has the highest environmental impact in all categories: ecosystem quality, human health, and resources. From the environmental point of view, MEMVR is the best alternative for wastewater treatment in shale gas extraction, because it consumes less electricity than the CMVR configuration, with a total environmental impact of 21.9% lower. The figure shows the comparison of the environmental impact subcategories. The problem is multi-criteria, since maximizing benefits implies maximizing the negative environmental impact. The figure shows the Pareto curve for the minimization of the Global Life Cycle Impact Assessment, LCA, environmental impact, and maximization of the gross profit. 4 points are considered in the graph. A is the maximum profit. B is the minimum global environmental impact. C is a point in which the profit decreases only 1.06% while the environmental impact decreases 13.5%, and D is the optimal solution when the model minimizes freshwater consumption. The table shows the optimal points on the Pareto curve for the simultaneous maximization of profit and minimization of the aggregated LCA endpoint impact. Individual values of the 3 endpoint categories, ecosystem quality, human health and resources depletion, are provided. The figure presents the Gantt chart for optimal fracking programs. A. Maximum profit and B. Minimal environmental impact. The number in each rectangle identifies the individual wells on each well pad. The figure shows the comparison of the environmental impact subcategories, using RECP endpoint, H, A, for the optimal solution for the best economic and environmental solutions. The table presents the well data for example 1. The 14 well pads, from A to N, are linked to the columns of the table. The figures show A. Flowback profile, and B. Production profile. For the example 2, the table presents the comparison between the optimal solutions, for the heuristic model and the optimization model, for the example 2. Optimization of hydraulic fracturing wastewater management, using hybrid multi-objectives linear programming. Hydraulic fracturing, HF, generates large volumes of wastewater, with a high level of contaminants during unconventional oil and gas production. Wastewater management supports sustainable economic development based on a hybrid multi-objective linear programming, HMOP, model. The goal is to simultaneously minimize the total cost of wastewater treatment, environmental impacts, and deviations from target constraints. The main limitations are the maximum concentration of total dissolved solids, TDS, and its maximum concentration in the wastewater treated for reuse or discharge. On-site treatment, deep well injections, and off-site treatment are considered as HF wastewater management strategies. The model identifies the optimal strategies in which the volume to be transported, and the volume to be returned for reuse is determined for wastewater. When the volume of wastewater is less than the on-site treatment capacity, the model recommends 2 strategies as optimal. The volume equals the on-site treatment capacity, 3,000 barrels of HF wastewater is delivered to on-site treatment, and the remaining volume to off-site treatment. When there is no demand for water for the next fracking, the model selects deep well injection rather than treatment options. Environmental costs have a significant impact on the selection of the optimal strategy. Similarly, pre-filled storage of 0, 30, and 50% did not affect the selection of optimal strategies. However, due to the increase in the level of TDS over time, The optimal strategy selection might be different for other cases. The model can be used for similar problems to optimize wastewater management in unconventional oil and gas production. The model was applied to 2 case studies that used real data for 31 weeks of operations. In 2012, 25% of total Canadian shale gas was produced in British Columbia at an average production rate of 2 billion cubic feet per day. The Canadian Association of Petroleum Producers estimated that 22% of total shale gas production in North America will be produced from Horn River and Montney basins by 2022. As shown in the figure, unconventional gas production in North American projects is projected to increase in the future, and 5 billion cubic feet per day will be produced per day from Montney and Horn River basins by 2022. Natural gas investment will significantly improve Canadian economy from 2012 to 2035. The Conference Board of Canada predicts $386 billion of Canadian dollar will be contributed to natural gas sector by 2035. British Columbia with $181 billion, and Alberta with $154 billion investment, are leading in natural gas projects. The overall objective of this study is to schedule HF wastewater to select an optimal management strategy in each period, that can be per day, week, or month. The figure shows the scheduling network to deliver HF wastewater from wells to storages, and then to wastewater management strategies. The wastewater treated from on-site and off-site treatment strategies are returned to the network for temporary storage in the tanks. The model can select the optimal strategy that is feasible according to quality and quantity of HF wastewater during each period. In practice, for each well, the volume of HF wastewater and the total dissolved solids (TDS) level are changing over time. Therefore, the hybrid multi-objective linear programming (HMOP) model can select several optimal strategies during different periods. In 2013, Adams described in Achieving Zero Discharge of Water in the HF Activities, the concept of the flowback water mixed with produced water to blend with fresh water, that are shown in the figure. Therefore, the HF wastewater is conveyed through the pressurized and membrane filter to remove TDS. After blending, chemical oxidation and electrocoagulation are used, to achieve the desired quality of water to be reused for subsequent fracture. The concept minimizes off-site trucking and treatment, volume of waste disposal and freshwater withdrawal in the next HF, which is a cost-effective strategy with less environmental impacts. The figure indicates the HF wastewater delivering network, which shows the sending of HF wastewater to treatment plant for reuse in the next fracking or deep well disposal. The network contains 2 phases. Preparation of hydraulic fracturing wastewater management operation network. HF wastewater is sent to the treatment facilities, and it returns to re-inject for next fracking. Wastewater management strategies. It starts when treated wastewater is reused, and again the HF wastewater will be transferred to the management strategies. In the first phase, the network involves a set of general components, represented by indexes. Wells, I. On-site HF wastewater storages, J. HF wastewater treatment strategies, K. Water tank, S, and freshwater, F. In the second phase, wells, H, and on-site HF wastewater storages, G. The HF wastewater is managed through 3 main strategies, which: Strategy 1 is on-site treatment facility. Strategy 2 is deep well injection, and Strategy 3 is off-site treatment plant. Freshwater is the water that is blended with treated wastewater and chemical additives to reuse for next fracturing. The network components are related to various colors arrows. The purple arrows express the amount of HF wastewater that is transferred to on-site storage. The green, red, and pink arrows present the amount of HF wastewater that is delivered from on-site storage to Strategy 1, 2, and 3 for treatment or disposal. The dark green and navy arrows indicate the amount of wastewater treated, Q, from either Strategy 1 or 3 which return to the site. Treated wastewater combines freshwater and chemical additives in the water tank to reuse for subsequent HF. Cooperation between oil supply chains, a games theory approach. Cooperation between oil supply chains powered by artificial intelligence is transforming the industry by creating digital supply networks, DSNs, that are more flexible, resilient, and transparent. This integration allows data to flow seamlessly between suppliers, refineries, pipelines, and markets, facilitating intelligent, coordinated decision-making in real time. Lloyd Stowell Shapley was born on June 2, 1923, in Cambridge, Massachusetts, one of the sons of Martha Betts, and the distinguished astronomer Harlow Shapley, both from Missouri. Shapley attended Phillips Exeter Academy and was a student at Harvard when he was drafted in 1943. Shapley served in the United States Army Air Corps in Chengdu, China and received the Bronze Star decoration for breaking the Soviet weather code. Shapley was an expert chess player, and an avid baseball fan. In game theory, Shapley value, named after Lloyd Shapley, who introduced it in 1953, is a concept of the solution in a cooperative game. For each coup game, Shapley's value allocates a single share among players of the total profits generated by the coalition of all players. The Shapley value is characterized by a collection of desirable properties or axioms. The game setup is as follows: a coalition or alliance of players cooperates, and gets a benefit that maximizes the maximum performance of the alliance. Some players may contribute more to the coalition than others, or may possess different bargaining power, such as threatening to destroy the alliance. Shapley's value sets the final distribution of the benefits of cooperation among players. Shapley's value establishes the importance each player has in global cooperation, and the reward they can reasonably expect. In this way, stable alliances are achieved. The Marcellus Shale play is dominated by a group of super-independents that have consolidated the region's core acreage to drive operational efficiency through scale. The figure shows wells from 12 companies operating on the Marcellus Shale play. According to the style of subsoil ownership in the United States, the ownership of wells is associated with the owner of the land, and projects must be carried out communally, when many land operators must operate together. Given the costs of operation, doing so individually can kill the profitability of projects. The first decision that companies must face is whether to act individually, or cooperatively. In the case of cooperative action, Shapley's theory is a way of dividing activities and the distribution of profits, in order to achieve stable coalitions. Variations of Shapley value. Because their exact calculation can be computationally expensive, various variations and adaptations have emerged for different fields. There are versions that modify how players are grouped or how they interact with each other. Owen's value, used when players form groups or priority coalitions before negotiating. It is useful in political or business situations where power blocks already exist. Shapley causal value, adjusts the calculation by considering the cause-effect relationships between the variables. It is used to avoid attributing importance to factors that are only correlated but do not cause the result. Bands have value, like Shapley's, but it does not consider the player's entry order, but simply whether their presence changes the outcome of the coalition, voting power. In this case, three strategies can be considered for the solution of the problem. A. Absence of cooperation, B. Full cooperation, and C. Cooperation. Three companies C1, C2 and C3 must choose how to act, to define a fracturing schedule for shale water management strategies. The figure shows the Pareto curve for the cooperation between oil supply chains. Life cycle impact assessment, LCIA, is normalized on the horizontal axis. The triangle-shaped, dark dots indicate uncooperative solutions, and circle-shaped, transparent, cooperated solutions. It is evident that the Pareto efficiency curve is made up of cooperative solutions, leaving only one of them outside the curve. All non-cooperative solutions are dominated by cooperative ones. Two limit cooperative solutions are distinguished. A is the minimum LCIA extreme solution, and D is maximum gross profit extreme solution. It is clear that cooperative solutions will produce greater benefits, and that the problem is how to distribute the additional benefits. This is what Shapley's theory is for. In the case of 8-player, the figure presents the optimal solutions, for water-related cost. The difference between the green and blue bars presents the extra utility earned by each player thanks to cooperation. For the cooperated case, the figure shows the expected optimal solution for each player. The figure shows the separation of expenses for the co-coppered and non-coppered solution. The cost savings turn into profits for the coalition. There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In the book Human Problem Solving, wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.